All right, Gen Chem people, we are going to do a lab today. So because of COVID and because we can't really come in and do the ball and stick models, some of you are coming in. We're going to do this using Phet, or Colorado Educational Science Modeling Lab. So let's get online really quick. And what I want you to do is I want you to type in Phet here really quick. So let's type in what we want. We want Phet. It's not typing in here. So we want this Phet Colorado. This is the thing that we want. And you're going to want to scroll all the way to the bottom. And you see these different bubbles that we can hit. This is chemistry class, so we're going to click on the chemistry one. And then we have all these simulations that we can use. So I want you to scroll down until you see the simulation that says molecular models. Okay, molecule shapes actually. So we're going to use this one right here called molecule shapes. This one in the middle, that's black. We're going to use this one. And you're going to get that to play. And we're going to use the model. Okay, now on this model, there are a couple of things that I want you to do. I want you to click the molecular geometry, and I want you to click the electron geometry. And I don't really care that you see the bond angles, but if you really want to see the bond angles, you can click that. I don't expect you guys to do the bond angles. I do expect the Gen Chem kids to know the bond angles. Okay, so we're going to use this simulation. Let's go back to this document that I have embedded in this module. This is the document that you're going to use to write down your answers to different things in the lab. And then you're going to use your responses in this document to answer the questions in the Canvas module. So the first thing we want to do is once we get into this Phet, we want to start constructing our table of how our shapes are going to go. So here we have number of electron areas around the center atom and how many of those areas are bonding. So I'm going to put in 4 single bonds on my Phet so that you can see what that does. So I want to put another bond. So notice I'm just clicking on the single bond here. So if I look at this, notice everything is 109.5 degrees apart from each other. So I can move this molecule around so that I can see what it looks like three-dimensionally. Notice down here, I have my molecule geometry, which is tetrahedral, and my electron geometry, which is also tetrahedral. So this is what we're going to want to put on our table here. We want to know the shape of our electron geometry, and that was tetrahedral. And our molecular geometry was also tetrahedral. Okay? For this next one, we still have 4 areas around the center atom, but in this one, we have 3 bonds and 1 lone pair. So let's go to Phet here. We're going to take one of these bonds away. So I want to hit that red X to take away one of those bonds, and I want to put a lone pair in there. So I'm going to hit this lone pair area. So notice I now have this, where I have 3 bonds and I have a lone pair. So if I look down here, my molecule geometry is trigonal pyramidal. My electron geometry is tetrahedral. Okay, so I want to put that on my chart. So I'm going to put that on my chart. My electron geometry is still tetrahedral, but my molecular geometry is trigonal pyramidal. Okay, so I want you to do the rest of these where you're looking at the number of bonding areas or electron areas, bonding areas, and non-bonding areas. Let's do the next one really quick. So number of bonding areas is 2 and number of lone pairs is 2. So I have 4 total areas of electrons. So let's do that. I'm going to take away one of these single bonds. I'm going to put in another lone pair. So I have 2 lone pairs right here and 2 bonds. Okay, so my 2 lone pairs. So if I look at that three-dimensionally, notice my molecular geometry here is bent. My electron geometry here is tetrahedral. Okay, so bent for my molecular geometry and tetrahedral for my electron geometry. Okay, so you're going to want to fill out the rest of this chart, and then we're going to use this chart to kind of guide us on some molecules that we're going to make. Okay, so I'm going to do the first one for you. We have carbon tetrafluoride here, so we need to figure out the total number of valence electrons to try and help us learn how to figure out how to do this Lewis structure. So carbon has 4 valence electrons and fluorine has 7. If you don't understand where I'm getting these numbers for, go back to look at some of the electron configurations and Lewis structures, the beginning ones. Okay, I've got 7 valence electrons on fluorine, but I've got 4 total fluorines. So I've got to multiply my fluorines by 4. So 7 times 4 gives me 28, plus 4 more gives me 32 total valence electrons. Now, the next thing I've got to do is I've got to decide what's going to be in the middle. And I choose the least electronegative atom except for hydrogen. And if we look at carbon and fluorine on our periodic table, fluorine is always the most electronegative. So carbon's going to be less. So I'm going to put carbon in the middle. And when I start, I'm going to start with single bonds to each of the fluorines. And then I want to create an octet. So carbon already has 8 valence electrons, right? Because each of these bonds are 2 shared pairs, or 2 shared electrons. So 2, 4, 6, 8 gives me 8 electrons already. So carbon's already done. Fluorine has 2 electrons because it's sharing, so it needs 6 more to have its octet. So I'm going to put in a lone pair. 3 lone pairs for each of these fluorines. So if I put in 3 lone pairs for each of these fluorines, then fluorine has its octet too. Remember, we always want to do an octet, or 8 electrons around each atom, except helium or hydrogen. They need 2. Helium and hydrogen just need 2. Okay, so now the thing is, we've got to count all our electrons that we've used. Have I used all 32 of my electrons? I have 2, 4, 6, 8. And aren't all these fluorines the same? So 8 plus 8 is 16, plus 8 more is 24, plus 8 more is 32. I have used up all of my electrons. Now, when I look at the center atom here, that center atom, carbon, has 4 bonding areas. So I'm going to go back to my Phet, and I'm going to put in 4 bonding areas, 4 single bonds. So I need 2 more single bonds. So now I have 2 single bonds. My electron geometry is tetrahedral, and my molecule geometry is also tetrahedral. So on my document, my electron geometry, tetrahedral, and my molecule geometry is tetrahedral. Now, the next thing to do is look at this shape and look at our electronegativities for fluorine and carbon. So if I look at let's go back to this one. If I look at my electronegativity for fluorine, I have 3.9 or 4.0, depending on what chart I'm looking at, okay? And if I look at carbon, I have an electronegativity, I'm going to use 4.0. I'm going to have an electronegativity of 2.5. So that gives me a difference of electronegativity of 1.5. Now that is pretty dang polar, okay? So that means I have electrons being pulled towards all of those fluorines because fluorine is more electronegative than carbon. Now, let's look at that three-dimensional shape. If I have electrons being pulled to all of these different fluorines, right, pulled there, pulled towards this fluorine, and pulled once again towards this fluorine, aren't these all equidistant apart? They're all equidistant apart. And all of these polarity on these bonds are all the same because it's all carbon to fluorine, carbon to fluorine, and carbon to fluorine, carbon to fluorine. Okay, so they're all the same and they're all equally distanced apart. So if they're all equal and all equally distanced apart, imagine yourself being pulled both ways by equally strong people. Are you going to move? No, you're not. And because this is all being pulled equidistant apart, this center atom is not going to be moved by those pulling forces. So even though this is really polar bonds, they all cancel each other out. Those dipoles cancel. So over the whole molecule, this becomes nonpolar. So we are going to write nonpolar for our answer here. Okay? So you're going to do this with each of these molecules. You're going to figure out the Lewis structure. You're going to build it in that Phet simulation. Get me the shape for both the electronic and the molecular geometries. And then look at those dipoles over that three-dimensional shape. See if those dipoles cancel. If they cancel, then that molecule is nonpolar. If those dipoles do not cancel, then that molecule is polar. That means we have one end that is a little bit more negative and another end that is a little bit more positive. Okay? All right. Have a great time doing this lab. We'll see you later. Bye.